Ladies and gentlemen, it is a rare occasion for me indeed to introduce someone who doesn't need an introduction. And I know this is a phrase which is used whenever somebody doesn't really know what to say, but this is the case where in reality we are welcoming here someone who doesn't need an introduction. Most of you here are computer scientists, or at least know about computer science bits and pieces here and there. I'm sure that we all know about quicksort, we all know about Hoare logic, we all know about data representation, we all know about monitors, we all know about CSP, you name it, many other contributions and ideas behind which there is today's speaker. We welcome here Professor Sir Tony Hoare, today of the Microsoft Research, but for long years at Oxford, earlier at Belfast, earlier at a computer company which not many of you may realize. The occasion is very special indeed in recognition of Professor Hoare's achievements and contributions to computer science. The University of Warsaw awarded him the doctorate honoris causa, which is the highest academic distinction our community can offer to any scientists. The celebration will take place on Wednesday. Unfortunately, the room is even smaller than this one, so we cannot invite everybody. The procedures are of a kind that there is an official promoter in the process. This time the role was taken up by Professor Turski. There are official reviewers. This time it was Professor Mazurkiewicz, who we have here in the audience, Professor Krawczyk of Technical University of Gdańsk, and Professor Idziak of Jagiellonian University. They all wrote very exhaustive, excellent opinions, praising extremely highly the achievements and contribution Professor Hoare has made over the years to computer science. When I look at the audience, it's absolutely clear to me that most of you have not been born when quicksort was born. So you should know that this is the person who has been a leading figure in computer science since more than half century ago, since basically ever on the scale of existence of computer science as we know it. This is really a person, one of the people who shaped computer science as we know it, and as we here at the Warsaw University try to teach you, the students of computer science, with much attention paid to the very special, solid, careful attitude towards software engineering, towards program construction, attitude based on concern for correctness, concern for quality, concern for the high standards we should maintain in our daily activities, whether as programmers, whether as scientists, whether as researchers, people. I think I shouldn't speak too long, although of course the list of achievements is much longer than I was able to say. Professor Hoare.
Thank you very much. Oh, thank you very much. I'm very flattered and very pleased to be back in Warsaw. Flattered, of course, by the offer of an honorary degree by the university, and pleased because Warsaw is one of the favorite capitals that I have visited in the last 50 years ago. I was here in 1960, approximately 3 or 4 months after the invention of quicksort, which I did in Moscow State University. And when I was coming home, I was offered a lift in a van coming through Eastern Europe and through Russia, because I knew Russian, and I could help the van driver and his colleague to negotiate the difficulties of hotels and borders in Russia, and I suppose to some extent in Poland. And I stayed, I think, in the same hotel that I stayed in last night, which was very comfortable, Bristol. And this morning I went again to visit the old city. Wonderful in this sunlight. Wow. Still, we're down to business. I start with a question, which I hope you will be able to answer better than I can at the end of my lecture. So, first of all, yes. And the summary is expanded by saying that you could test the understanding of a computer in the same way that you test the understanding of students, or I should say it the other way around, in the same way that the understanding of students is tested by an examination, nowadays usually a written examination, the old days, and to some extent even now an interactive examination, in which they're not only asked to answer questions, but they're judged far more of their understanding depends on their ability to justify the answers to the questions that they give. Already in primary school, well, secondary school anyway, students are asked to show their working. And if you give the right answer without any working, you don't necessarily show any understanding, and certainly you run the risk of giving the wrong answer, from which maybe the examiners will conclude that you have no understanding. But if you've shown your working, then your working can show the understanding even when the answer is wrong. So the computer will pass the test, has to achieve a certain mark to pass the test. I'm not going to give a numerical mark to the computer, but if professional programmers are able to use the computer as a sort of intelligent programmer's assistant in the design and development and delivery and testing and maintenance of their programs, then I think we would be justified in using the word, in saying that they had passed the test. This happens to some extent at the moment. We all use compilers to help us write programs, but we don't believe that the compilers actually understand our programs, because they don't give us enough assistance. They can't justify what they're doing. Oh, let's see. In making my thesis that computers could understand their programs, I'm going to mention something about Aristotle and Euclid, and then refer to two very important articles by Turing, both of which were more than 10 years before I even entered the field of computing. His a paper on checking a large routine, in which he invented his assertions, and his paper the next year published in the British Philosophical Journal about computing machinery and intelligence. So, starting with Aristotle, Aristotle is regarded as the father of deductive logic, and he defined it very much in the same way that we define a logic these days. First of all, by giving a notation and a syntax for each relevant concept to be used in a proof, a grammar in which you can justify each line of the proof by referring to preceding lines in the proof, and a grammar for each valid deductive step, so that you can check the correctness of a proof locally by looking only at the conclusion, by referring only to two previous lines of the proof, the premises of the deductive step, and the conclusion. And if these form a syntactically valid, a grammatically valid syllogism or step, then the whole proof is valid no matter how long it is. These ideas were due to Aristotle, as far as we know. So, let me introduce you to Aristotle's grammar. Has anybody studied the grammar of Aristotle? So it won't be too familiar to you then. He said, let S stand for the subject of a sentence, and let P stand for the predicate of the sentence. And he defined the grammatical forms of 4 kinds of sentence. All subject are predicate. No S is P. Some S are P, and some S are not P. And these were given 4, well, I think later they were given 4 mnemonic letters, A, E, I, and O, which I'll show you they were used later to help remember what the valid syllogisms actually are. Here's the first syllogism that everybody used to learn in universities. I'm sure they learnt it in Warsaw. The 2 premises, all S are M, which is of type A, and all M are P, which is of type A. Those are the major premise and the minor premise, and the conclusion is all S are P, which is also the form A. And that explains why this syllogism is called Barbara, because the 3 vowels in the word Barbara are all A's, indicating the pattern of the 3 lines of the syllogism. Here's another one, Kellarent. No M are P, that's an E. All S are M, therefore no S are P. You have to just think a little while to realize that this syllogism is valid, and maybe it helped to draw a little diagram, a little Venn diagram that we would do today. And third one, Darii. As you can see, it has an A and an I and an I. Example, all M are P, some S are M, therefore some S are P. Well, there are 24 syllogisms, and there is a list of them. And a graduate of Oxford University would probably know them all extremely well. Modern logic is a little bit simpler than ancient logic. Many modern logics have just one rule of inference, modus ponens, and just a couple of basic axioms, at least at their foundation. Of course, there are rather more axioms to deal with more powerful forms of reasoning. Now, the main application of Aristotelian logic, I think, was probably in biology, because Aristotle was the father of biology as well as the father of logic, and he was the father of classificatory biology, which was the main form of biology right up until the modern era. And he was classified the animals and fishes that he saw in groups, in genus and family and kingdom. And here are some examples. He was, while he was on his travels before founding his academy, he visited the island of Lesbos, and he used to ask the fishermen as they came in the morning to name all the fishes in their catch. And he looked at them carefully, and he decided that the sharks and the rays were rather different from most fishes. He called them syllogisms, and so that's gave me the subject matter of this example. All sharks are syllogisms. All syllogisms inhabit the sea, therefore all sharks inhabit the sea. Kellarent, example, no syllogisms are fish. All rays are syllogisms, therefore no rays are fish. And here's a proof which only has 5 lines, so it only has 2 syllogisms, as shown here, and it has, I think, 3. All sharks. It has 3 premises, I think. Yes. We'll have a look at it. Anyway, a proof can be as long as required, and some of its lines are going to be premises, like the first the first, second, and fourth of these, and some of them are going to be intermediate conclusions, like the third line, and some of them are going to be final conclusions of the proof. Well, just one of them usually is the final conclusion. So a proof is a sequence of sentences in which each sentence is either a premise or is the last line of one of the 24 syllogisms, and the first two lines of that syllogism occur earlier in the proof. This is not the definition that Aristotle gave, I don't think, because Aristotle believed that you couldn't have the same term that you are defining on the left-hand side of your definition is not allowed to occur on the right-hand side as well. Modern computer science has sort of rather forgotten that old tradition of definitions because we're so used to recursion, of course. Now, all this seems very familiar today, but I think we should realize quite what an immense leap of progress it was to formalize logic in the way that Aristotle did. See, if you examine the man in the street, the person who had been untaught by Aristotle and other logicians, and ask them whether a proof is valid or not, whether the proof was correct or not, they'd be very likely to say, well, what's the proof about? That's irrelevant. They would be likely to ask, what is the result? Is it true? That's irrelevant too. Is the result desirable? Am I going to like the result? Irrelevant. Who is presenting the proof? That tends to make a lot of difference to whether people accept an argument, whether they like the person who's presenting it, or like the conclusion of the proof, rather than whether it's valid. It's even independent of the truth of the conclusion and the truth of the premises. It depends only on the syntactic form of the proof. And because it is only the syntactic form of the proof that you need examine, this is the reason why computers are so good at proof. You don't need to know anything about the external world. Computers really don't understand the external world very well at all. But they are very good at checking syntactic correctness of programs and proofs and other things that can be expressed as sequences of characters. So, if you have a logical system, a deductive system, then the correctness of the proofs can be very readily established by computer, and computers can explore to discover proofs by enumerating all the possible next lines of the proof and proceeding in that way, and generate an enormous number of proofs from the proof rules which nobody is ever interested in. But if eventually they came across a conclusion that you were interested in, then the proof would be a valid proof of that proposition. Now, computers were used for teaching logic for many years, but in recent years, last 10, 15 years or so, they've actually begun to be used by mathematicians as an essential aid to constructing proofs. The four-color theorem, which was posed many years ago, has resisted all human attempt to prove it for over 100 years, I think. Finally, in Canada, it was shown that it was true. There was a lot of difficulty about believing the proof. It was a very long proof. It came in two parts. Part of it was a mental or manual done by the mathematicians. They reduced the proof to examination of 1,800 cases. 1,800 little diagrams that you can draw, and if all of them can be colored with 4 colors, then you're okay, the theorem is true. But in order to prove 1800 cases, they used the computer. Let's have a look at the 4-color problem. You probably know it. On the left-hand side, there is a map that can be colored by 4 colors. You'll see that 4 colors are necessary because the green square has to be different from all the surrounding squares because it's obviously a neighborhood of that color cycle. And the perimeter of the green square all has to be different because every state in the perimeter touches each other. If you make a more complicated diagram, is this still true? Well, fortunately, the more complicated diagrams that I've shown on the right, for example, I've split Texas into 2 parts, and now it's actually easier to color. You only need 3 colors. Does there exist a map that needs more than 4 colors? And the answer is, as the computer has told us, is no. So, the proof has recently been recast into a proof that is done entirely by a computer. So the initial analysis of the 1800 cases has now been done by computer, and in fact done rather cleverly by Georges Gontier, who's a colleague of mine at the moment in Microsoft. It turns out that you only need to examine 633 cases, but each case requires around 1 million proof steps. And that really makes gives you a good reason for using a computer in this proof. More recently, Tom Hales has tackled the Kepler conjecture, again by a joint proof by hand and by computer. The Kepler says that if you have a large volume, a large number of oranges, the easiest way to, the way that will fit most oranges into a given large space is the natural way that they will assume anyway, where each orange fits into the dimple formed by the 3 oranges just below it. And that will pack the most oranges into the... Hales is now engaged in a larger project called the FlySpec project, which is attempting to computerize the whole proof. And this is a major undertaking with the present tools, proof tools. The latest estimate that I saw on the web, it requires a lot of manual assistance to get the proof into a form which the computer will accept. The proof has to be formalized. It can't be done by hand waving or by intuition. And that takes a long time, and they estimated that there are still something like 66 man-years of work before we can claim that the computer can prove that conjecture. Right, my next logician or mathematician is Euclid. Very little is known about him. He worked in Alexandria in Egypt around 300 BC. And his textbook, like the texts of Aristotle, were used in education for thousands of years. In Europe more recently, but in Middle East, Arab countries and further north, Central Asian countries, even before it was rediscovered in Europe. And Euclid was quite a great mathematician. He did a lot more than just geometry, and he even invented the example that we all learn at the beginning of our courses, the algorithm for the greatest common divisor. So, I maintain that Euclid was the designer of the world's first programming language and the world's first user of a programming language in which every program could be proved to be correct. There aren't many people who have designed programming languages, even today, in which every program can be proved correct, but Euclid was one of them. It's because all of his proofs are constructions. They tell you how to do something, how to draw a figure or a line or a point which satisfies some desired property, and at the same time give a proof that it does satisfy it. So the construction is written in a programming language, and the programming language has usual constructs, assignments, sequencing, subroutines, parameters, preconditions and postconditions, but not loops. His classical geometry did not know about iteration. Well, he knew about iteration, Archimedes knew about iteration, but it wasn't part of the standard Euclidean canon of geometry. Things that you do with a string or a piece of paper, sort of nudging the paper into place so that it satisfies a given property, that's a construction which isn't recognized by Euclid. And every one of his proofs proves the correctness of a program. Well, very nearly every one. Like Aristotle, he started off with a logic, a system of inference that started with axioms, which tell you, first of all, what things you can draw. So this is a formal definition of Euclid's programming language. It is a primitive function of the language to draw a line between 2 points. The existence of such a line and the possibility of drawing it are included in postulate number 1. Postulate number 3 says, given any point and any radius, we can draw a circle around that point with that radius. And the 5th one is the parallel postulate, which has since come into, well, been called into doubt, shall we say. And those are actually the five basic actions of the language. The ones in ... I'm not going to use, so I won't describe them any further. Here's a picture of how you can draw a circle around a line with a piece of string and a post, which is or a drawing pin, which is holding the line at the center. Then he supplements his postulates by 23 definitions. First of which defines a point as that which has no part. Number 15 defines a circle, and number 16 defines the center of the circle, and number 20 defines an equilateral triangle as a triangle with 3 equal sides. And these definitions relate the words of the language to each other, and I think to their meaning in the real world. Some of them, like number 20, are formal definitions, but number 1, I think, is actually saying what sort of thing in the real world is meant when the theorem is talking about a point. And that's a very important part of applied mathematics. So here's a pictorial illustration. I'm going to use mark lines which are equal to each other with some symbol. So that diagram is a triangle, and the fact that the 3 lines have the same marking indicates that they are equal. Now, if you look at those 3 definitions, what they in fact say is that all straight lines from the boundary of a circle to the center of the circle are equal. And maybe that should have been a postulate. But in fact, the statement is a summary of 3 definitions, 14, 15, and 16. Unfortunately, the 3 definitions would, if you wrote them out formally, would be mutually recursive. So I've put those 3 definitions together, as it were, as a single statement, which I will be using shortly. In addition to the postulates, which are the sort of basic actions of the program and the basic steps of the proof, and the definitions, he also had 5 common notions. Common notions, he realized that geometry was only a branch of reasoning, and therefore there were other branches of reasoning other than geometry. The common notions are the notions that are common, shared by all branches of reasoning. And they are very interesting. 2 things that are both equal to a third thing are equal to each other. It is going to be valid in any reasonable branch of reasoning, expressing, of course, the transitivity of equality. If equals are added to equals, the wholes are equal, the sums are equal. If equals are subtracted, similarly, things which coincide are equal. That is, if you look at the same line on a diagram twice, the 2 lines that you see will be equal. And finally, the whole is greater than the part. So, let me give you an example of a Euclidean proof, which says to construct an equilateral triangle with a given side. That's not a theorem as we normally think of it. It's a subroutine. It's a subroutine that you call to construct an equilateral triangle with a given side. If that's what you want to do, here's the recipe for doing it. And in book number 1, there are 48 propositions or theorems, ending with Pythagoras' theorem. Propositions, as I said, are subroutines which can be called from anywhere in another or later proof to perform a useful construction. And the proven properties of the construction can then be used as assumptions in the proof of any proposition that calls it. So here we have the rest of his books are building up a library of programs which are useful and all of which actually satisfy their specifications. And so it's a big mathematical and intellectual structure which he has built and on which all geometry, well, most of geometry is also built. So here we are, a proof. Here is the construction is of an equilateral triangle with a given line as one of its sides. Choose one end of the given line. Draw a circle round it. Choose the other end of the same line and draw a circle round it. Does anybody know this proof? Yes, everybody. Only the people who laughed. Put up your hand if you know it. Oh, wonderful. Great, great. Oh, that's fun. So, choose one of the points of intersection of the circle and one end of the given line and draw a line between them, and similarly for the other side. Now we go on with we claim that the triangle in the middle is equilateral. The proof uses definition 15 to take 2 radii of the left-hand circle and claim that they're equal. And then similarly, you can claim that 2 radii on the right-hand side are equal. And finally, remember common notion number 1, 2 things that are equal to the same thing are equal to each other. And so all 3 of them are equal. Lovely. And now we can rub out the construction, and we're left with an equilateral triangle. So he invented, as it were, local variables, which don't have to be used outside the actual proof of the particular proposition. So here's a summary of the various features which I said at the beginning Euclid's language actually had. Choose a point and give it a name C is rather like an assignment. Implicitly, whenever you give two instructions, one is done after the other. That's a sequencing or semicolon. Subroutines and preconditions given a straight line, and postconditions. The triangle is equilateral. So let's move on to modern times, skipping nearly a century and a half, 2 centuries and a half, to Alan Turing. And the reason for doing that is that this is the year in which we commemorate the centenary of Alan Turing's birth. So why not miss out everybody in between? Alan Turing invented a logic for reasoning about programs, and as a consequence, the computer can use that logic to answer questions about its own programs and can justify its answers by proof. So essentially, this is going to be the basis or framework of the case that I want to make, that computers can understand their own programs. So instead of Alan Turing, of course, writing in 1949, didn't know of any modern programming languages, so he had to use the flowcharts. And I'm going to give you a modern update of what Alan Turing would have said nowadays to make it look a bit more like Aristotle's syllogisms. The basic primitive notation which I introduced used curly braces, and each step of each line of the reasoning has not just 2 parameters, not just a subject and a predicate, but 3. 2 predicates and an action which is indicated by a verb or V. The idea is that V, being a verb, is something that changes a part of the real world. P describes the initial state of that part, and R describes the final state resulting from an action V. So all these Hoare triples are the primitive lines of a Hoare proof, or perhaps I should really call it a Turing proof. Here we have some examples. When the radio whistles, turning the knob ensures the absence of the whistle. When 2 distinct points are closer than R, then drawing a circle of radius R around each point ensures that their circumferences intersect at 2 places. That's something that Euclid never said. He should have said it in the proof of his proposition 1. I'm not going to prove it for you, but at least it gives a good illustration of the triple that is the basis of reasoning about programs. And the third one describes an axiom of assignment. Increasing the value of x ensures that it is one larger at the end than at the beginning. So now, let us phrase in Hoare logic in the form of Aristotelian syllogisms, which is what I did. If you know that when P is true, V1 ensures R, and you know that when S is true, V2 ensures R, then the sequential composition, V1 then V2, also ensures R. Conditional tests tells you how to construct a new verb which combines the power of 2 previous verbs and a condition which has to be true to select between them. Repetition. This is something that Euclid did not formalize. And non-determinism. Euclid knew about non-determinism because his proofs have non-determinism in them. For example, when we selected the vertex of our triangle and called it C, we could have selected the other vertex. This is an important feature of his method and of proofs, that you are allowed to make choices in your construction, and your proof will apply no matter which choice you make. Provided you followed the rules, you can make either choice. Now this is very interesting when you actually apply Euclidean geometry to what it was applied to at the time that he invented it. For Euclid geometry, well, for the Egyptians, shall I say. I don't suppose Euclid went out to measure fields very often. The Egyptians were great architects. They were able to draw a plan on the surface of the earth using stakes and ropes and sticks to make marks in the sand. When they were surveying, either in order to make a building, or indeed to make a map, or indeed just to indicate where the edges of the fields are after the Nile has flooded, they could use Euclidean geometry to make their squares really square and their circles really circular and so on. Now supposing they wanted to draw an equilateral triangle with one side along the bank of a river. They draw it, and they draw the two red lines in construction. Which side of the river do they draw it? Well, obviously the same side of the river. The non-determinism is useful because it's given the person who is implementing the procedure a choice of choosing whichever is most convenient. And whichever he chooses, the same proof will apply. And that's the way we have to control non-determinism in our programs. We can't test a non-deterministic program exhaustively. There are too many combinations. But if we've proved its correctness, we know the proof will be valid in spite of whatever choice is actually made to resolve the non-determinism. So here we are. The rule for non-determinism, which I didn't put in my original article. If V1 and V2 satisfy the same specification, then V1 or V2 satisfies the same specification, which is exactly what I've just said. So let's get on to Turing's other article, the Turing test. I expect you all know what the Turing test is. It's a conversation between a tester and a machine in which the tester chooses the topic of discussion and the tester asks all the questions, and the tester is given 5 minutes to say whether he's talking to a machine or a human being. And Turing thought that one day computers would be able to pass this test by fooling the machine on 30% of the tests. At 30% of the occasions on which the human being said it was a, which the tester said it was a human being, it would be a computer. Sorry, I've got the wrong one. 70% of the time, the tester would be right, but 30% wrong. Am I? Oh, I forgot. So it's actually a sort of, and the tester is not a computer scientist. Now, of course, there have been prizes set up for machines that could pass this test. And every year there's a competition in which people enter their machines, and a panel of testers asks the machine, and usually they know after the first question that it was a computer. In just one case, they made a mistake, and that was when they thought the human being was the computer. So, and it turned out that was a deliberate attempt on the part of the human being, because he thought he'd been asked to behave like a computer. So, let me just give my version of the Turing test, in which we preserve Turing's original idea of an interactive or conversational test, but there is only one subject of the test. We're testing its computer science. In fact, we're testing just its software engineering, understanding of software engineering. And its own programs are the only things you're allowed to ask questions about. But the tester can ask as many questions as desired. And the machine passes the test if the tester is persuaded to go on asking questions because he or she is interested in the answers. That's the real test, that you can actually get interesting answers out of the computer, which, if you are a programmer, you can use to help you write your programs and get them correct. So the criterion of understanding is that the machine doesn't have to give an answer to all questions, because Turing knew very well that a machine could never answer all questions successfully and correctly. He was the person who discovered this fact, after all. So we won't require an answer to every question, just as we don't require an answer to every question from every student of our examinations. But the important thing is that a given answer is correct and that the machine can explain the reasons behind it. Why is it true? Additional criterion is that most of the answers, again not all, are relevant and useful to the programmer, the software engineer who is writing or has written the program about which the computer is being examined. So, what sort of questions would we like to ask about when we submit our program to the computer? Can the program overflow a buffer? Buffer overflow? Buffer overflow. This was a very important topic when I first joined Microsoft in 1999. The writers of viruses were all exploiting buffer overflows, subscript overflows, to inject malicious code into the computer. And there were two notorious viruses, Code Red and one other, which basically shut down all the computers in the world by spreading around the web for several days, 2 or 3 days. They shut down all business activity for that time at a total cost to the world economy estimated at $4 billion. I regret to say they were using Microsoft software, and Microsoft made a very heavy investment in writing programs that would answer this question and using them. Now, if the answer is yes, if there is an error there, you want an explanation. Why did you say yes? Because of this. If you set the value x to this, and if you set the value y to this, and you follow this path, then you will get a buffer overflow. You could ask a computer that generate test cases that exercise all the changes that you've recently made to your program. In Microsoft, most programmers spend most of their life making changes to existing programs. You make a small change, you test it. If the computer could answer this question, it could then generate tests that would reveal all the faults in your program, and you wouldn't have to construct test data. Can this change make the program slower? If it does, make it seriously slower, then you can't deliver the program, as the customers will reject it. Are all the assertions made in the program valid? Could aeroplanes under control by the program ever collide? That last one is quite a challenge. I don't think we've had very many computer check proofs that our air traffic control systems are correct. But the amount of testing that is done by the airplane companies suggests that it is correct. They put 4 times as much money into testing as they do into design all other phases of program construction. If we had this machine, then that would save an awful lot of money. Here's a prediction. Alan Turing predicted that his test would be passed within 50 years. In fact, he gave his reasons for that belief. He knew the size of the Manchester computer at that time. It had several thousand bytes of store and an operation speed of thousands of operations a second. He said if that were only 10 times faster, we could do it. And he predicted that a program that did it would take somebody 50 years to write, 50 man-years. Mind you, if the man was Turing, it might well have been right. But it has certainly not proved to be possible to do that on the machines which are well over 1 million times faster, 1 million times larger than the machine that he was basing his estimates on. However, here's the next prediction. Within the next 50 years, the design automation system for software engineering will be widely used by programmers in all phases of the life cycle of a program to generate and test and maintain and update and correct the ubiquitous software of tomorrow. I've attributed this to J. Moore, who called such a program the intelligent programmer's assistant. And this will be a collaborative development, not like Turing's test, which is essentially an adversarial test, not like the exams that you do for your university, which sometimes seem to be rather adversarial. Your examiner is trying to get you down. But this will be collaborative, because the things that computers and humans are good at are quite different. The human understands the real world. The human understands the needs of the users of a program and the commercial opportunities for selling the program. We do not wish to teach the computer those things. The computer understands the consequences of human decisions in the context of a large and complex program. So the computer is doing the logic. It can deduce from what has been given to it what the answers to the questions are, but it doesn't know why you're asking the questions. However, let me make another prediction for 50 years' time. When it's all working, the constant complaint of the program is, the computer doesn't really understand what I want my program to do. It only understands the easy part of my job, and sometimes not even that. Because we all complain about our tools. The development of the programmer's assistant will, I'm sure, always admit further improvements and adaptations to suit the needs of particular applications, particular programs, and particularly programs for new applications will all require development of the programmer's assistant in order to be able to give that assistance. Let me just... and so I think you could probably conclude that there will be plenty of employment for computer scientists for the next 50 years developing that, and at the end of 50 years there will be just as much work making sure that it's kept up to date with the needs of programmers of succeeding centuries. So, if you followed my reasoning and agree with it, I believe that we will say routinely, without worrying, that computers understand their own programs because they satisfy this analogy with human understanding, that they can explain the reasons for the answers to the questions. But what does it really mean to say that computers understand? After all, we'd also say aeroplanes fly. And that's not a very controversial statement about aeroplanes. And it's justified by an analogy with the flight of birds. But we don't say that submarines swim. But actually, when you come to think of it, swimming submarines is much more like a fish than the aeroplanes flying being like a bird. Because aeroplanes don't flap their wings. Submarines at least have fins. But we don't say this. So it's largely a matter of fashion, the way that language develops. How is language going to develop? Is it going to develop to say submarines swim, or is it going to say aeroplanes fly? These are. But we don't ask, do aeroplanes flap their wings? Do they lay eggs? And therefore I am not going to ask whether a computer is intelligent or not. Because I think I just don't think that's an analogy that one should push too far. I think Turing really was motivated by proof of the intelligence of computers. I am demotivated by that. I do not want my computers to be intelligent. Not in the normal human sense of intelligence, but understanding of logic and understanding of computing and understanding of programs, those are the attributes that I want my computers to have. Thank you very much.